Hello everyone, this is the video lecture for Linear Algebra Chapter 7. We're going to be talking about eigenvalues and eigenvectors. Okay, eigenvalues and eigenvectors. That's all of Chapter 7. That's what it's about. This is the last chapter that we're going to be covering in this class, but you couldn't take linear algebra without seeing the eigens. So we're going to definitely talk about the eigens, eigenvalues, eigenvectors, and what they do and how they work. Let me go ahead and give you kind of like a definition of what we're going to be talking about. So we got AX is equal to lambda x. Okay? Now that lambda, it's a Greek letter for L, lambda, and it's a scalar. It's just a number. Just a number. In fact, there's going to be a few lambdas per matrix, but this is what's called the eigenvalue. And there's a couple different ones of them, depending on your matrix. These x's right here, that vector, is called the eigenvector. Now, the eigenvector is associated with a particular eigenvalue, and vice versa. So if you had, and we will eventually have, like, say, 1, 2, and 3, well, then you would have x values. You'd have one for that one for this, and one for that. However many eigenvalues, you have that many eigenvectors. Maybe there's another, like, more of these or more of those. I can't remember it, but they're associated very closely with one another, and so you got a lot of eigenvalues, you got a lot of little eigenvectors. So it's not just a singular number for each one of those. So eigenvectors. Sorry about that. Okay, so let me just go ahead and do it. For all x, such that ax is equal to lambda x, this set here, I guess they're just x, such that you got this, that's equal to the eigenspace. I don't use that term very often myself, but it's basically the eigenvectors all kind of put together. So if you had a lot of eigenvectors, you would basically just put it all in the one big matrix kind of thing. Or I guess you don't have to. You can also keep it as a set, but okay, so eigens, a single value and a vector that somehow make, and this is why it's kind of weird, you're actually going to be multiplying a matrix by the vector by a matrix, and you get a scalar of the original. Let me just do like a quick little example of what could happen. So this is something that just could happen. Let's say that I got, I don't know, 2, 2, and 2, and I'm going to multiply this by 4, 5, 6. Okay. So this times that. You do the math, blah, blah, blah. Basically, you're going to get 8, 10, and 12. Notice that these guys are linked somehow. They are scalar multiples of one another. You could say that this is 2 times your original. And that's where that's a lambda, and that would be your eigenvector. And so there you go. What's kind of interesting, though, is that because you could see this diagonal matrix has this number right here, these diagonals are actually the key to finding your eigenvalues. It's not a mistake that this is a 2 right here because you got 2's right there. It's kind of like just because you have 2's right there, you're going to get a 2 eigenvalue. So we're going to be looking very closely at the diagonals as we keep going. Okay, if all this is kind of weird, let's just kind of jump in to I have one last definition, and then we're going to do some problems. And so ways to find these eigenvalues and eigenvectors, there's 2 formulas, I guess you can say. Lambda I minus a, find the determinant, and set it equal to 0. That's one way, and that's often the first way, and I often use that to find eigenvalues. To find the eigenvectors, I often use this formula here, and I say it's equal to the 0 vector. Now you would think, oh, that basically says the same thing. Determinant equals a single 0 versus a 0 vector. Sure, And whenever you rearrange it, you get the same thing as what's up here. I mean, it's no different. You just put an I right there, and it's the same exact same formula. So that's fine. But this is more helpful initially, and then you build using that one right there. So these are going to be very helpful as we keep going. Okay, so let's do, I think this is a proof. Yeah, let's do a proof. So I got for an invertible matrix A, prove that A and A inverse have the same eigenvectors. Okay, now hold on, big pause here. When I started writing this, copying it down from the book, I thought it said eigenvalues. I mean, eigenv, and just a few little letters are changing the whole thing. It is not correct to say that they have the same eigenvalues. If you put values right here, that would be incorrect. You can't do this. This is not a good proof. But eigenvectors is okay. Kind of weird. And I'll show you why and what that means here through the proof. Okay, we'll talk about the eigenvalues in a little bit. But because they're focusing on eigenvectors, personally, again, this is my go-to for value, and this is my go-to for vector. Not necessarily all the time, but that's what I'm going to use here in particular. So I'm going to start with that. I'm going to say that I got lambda I minus a x is equal to 0 vector. Cool. What's interesting, though, is that they're saying that I want to prove that A and A inverse have the same eigenvector, that x. So it should be the same. So my proof, then, is going to be involving this inverse somehow. Let me go ahead and just say that this is going to be eigenvalue 1, and this is going to be eigenvalue 2, just to make sure, just in case. And then I'm going to say this is my inverse. I'm going to use a y. So notice that my eigenvalue and eigenvector have changed, okay? But really what I'm wanting to do is prove that my x is equal to y. Prove that x equals y. I guess you could take like all of this right here and summarize it in this format. So I'm taking the English and I'm putting it into math for you. I have this. Prove that x equals y. Prove that these guys are the same thing. So how do I do that? Well, let's just start with this one and start manipulating it. So I'll start with this. Let's go ahead and distribute my x. And I'm going to move this guy to the other side. What you get is, well, the definition that you had way earlier. You don't need an I in there if you don't want to. The I is basically a 1. Doesn't change anything. So there you go. Look, by definition, we have my eigens. Eigenvalues, eigenvectors. Okay, well, that was cool. Now what? So we proved that we have eigens for A. Well, don't go and do anything right here now. I'm wanting to link this back eventually. So I'm going to continue on. What's the biggest difference between these two right here? It's my A versus A inverse. That's the biggest difference. Okay? And so what I'm going to do is try to find I'm going to get A inverse out of this somehow. So I'm going to multiply by A inverse on the left side. Okay? And this is where I is actually pretty handy. You don't have to have an I, it just kind of helps. So these guys make an I. And this is a scalar. I can move that out to the front. This also should have a 1. You can have an I there or not. It doesn't really matter. There you go. Cool, cool. Let's go back up for a second. Notice that we got this A inverse. We got a Y thing going on there. It's looking pretty close. I got an inverse-y thing here. Let me kind of keep going for a second. I'm going to actually divide this to the other side. So I got A inverse x is equal to 1 over lambda 1 ix 1 over lambda 1 x. Okay, now big pause, big pause. Notice this definition right here. That's still just a scalar. I don't know. let's just say that lambda 2 is equal to 1 over lambda 1. Wouldn't I then have what I should have had for this guy? See? Oh, right. I guess you could say that this was a y value now. You don't have to. I mean, obviously x is equal to x. So we got the same eigenvectors, but notice that my eigenvalue is different. So if I had 2, well, now it's like 1 over 2. It's 1/2. So different eigenvalue, but the same eigenvector, literally x. Hadn't changed the whole way through, okay? So, well, you're done. That was it. Proven. Okay. Next section. 7.2 is diagonalization. Diagonalization, okay? So, diagonalization, we got a diagonal matrix, which I'm just going to use D. It's very convenient to use D. It has values only in the diagonal. So values only in the diagonal. So what does that look like? So here's a quick little example for you. 1, 0, 0, 1, 2, 0, 0, 0, 3, something like that. Notice that my diagonals, I have a single number for each row and column, essentially. And it's on the diagonal. Cool. So the definition of diagonalization is A is diagonalizable when it is similar, there's a key word there, we've seen that before, to a diagonal matrix. Okay, so let me show you what that looks like. Basically, D is equal to P inverse AP. Diagonal is equal to this stuff. And of course you can rewrite this to put the D in the middle. It's all the same. So I guess you can just, I'm going to real quickly write what the other version would be. But if you remember our discussion on similar, I mean, you can write the inverse here instead of there or whatever. It's an arbitrary P matrix. Either one of these is fine. Okay. So let's do a proof. So I have a proof that if my A matrix is diagonalizable, it's a big word, with, and this is where it's interesting, real eigenvalues, lambda 1, lambda 2, so on and so forth, lambda n all the way down, then the determinant of A is equal to lambda 1 times lambda 2 times lambda 3 times da 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 da, all the way to lambda n. Okay. The word real here is actually important to some degree. You would think, oh, well, I mean, we got real eigenvalues here. It's not fake ones. They're not trying to say that. They're trying to mean it when they say the real, they're trying to mean the reals, as in like scalars. They're saying scalars right there, okay? So just keep that in mind. So how are we going to go and do this problem? Well, they're talking about it being diagonalizable. Prove that if it is diagonalizable, then with these eigenvalues, then I have a determinant. So I can actually start with the diagonal myself. Or again, we can start with this one. Either way is fine. If I want to start with this guy, notice that my end goal is to somehow prove this determinant. So I'm going to actually just take what I have there and do a determinant on both sides. So I'm taking this one, and I'm doing the determinant on both sides. Well, that's not going to change, but this is an interesting little guy here. So what I'm going to do is I'm going to split it all up, and you'll see that I can do determinant times a determinant times another determinant, because, again, going way back to like chapter 2 stuff, the determinant of AB is equal to the determinant of A times the determinant of B. Basically, you can distribute your determinant between all these matrices, and that's what I just did here. So that's not too bad. Well, I want to keep going, of course. There's going to be a little bit more math here. I'm going to rewrite this one here as 1 over the determinant of P. Again, because, going way back to chapter 2 stuff here, the determinant of A inverse is equal to 1 over the determinant of A. Okay, now I probably should not use A and B here, but that was just, it's a rough proof now, but it still works. The idea is that I'm trying to remind myself how I can do some of these problems. Well, notice here that my P and P inverse are going to cancel. I'm not going to truly keep the canceling, but you can see that it's going to cancel and be left with this guy. Okay. So, period. We're not completely done. What we just proven is that the determinant of A should be equal to the determinant of D. D is a diagonal matrix. Lambda 1, lambda 2, lambda 3, and so on and so forth, is actually what's going on here. Now, I know there's a ton of zeros and stuff here. Okay. Why am I putting lambdas in the diagonal here? Well, this is where it's kind of interesting, because my diagonal matrix is and should be my eigenvalues. I know that there's somewhere in the section where it would say something like this. I don't have it written down, but I should probably say something about the eigenvalues are the actual diagonal elements of D, that kind of thing. I just don't have, I don't have like a property, by property, whatever, 7.3 or something like that. I don't really know. So it's there, it's somewhere, but basically what's going on is that my determinant can also be found by multiplying my diagonals for a upper or lower triangular matrix. So I'm doing a lot of English here that I'm not writing down for my proof, but basically my determinant of D should be the product of my diagonal elements. And because it's a diagonal matrix, I know it can do this. So therefore, notice again, they're equal, right? This is also equal to the same thing. There you go. The end. Because again, I know this one worked for D, but now, because D and A are the same determinants, so then therefore I can say that's the same thing for A. Okay. A little bit of rough proof there, but it'll still work. Next section. 7.3. Symmetric and orthogonal matrices. Oh, orthogonal diagonalization. Sorry. There's always another word for it. Symmetric and orthogonal diagonalization. These are actually terms that we saw way back in chapter 2 and 3 and whatnot, and they're kind of like side notes, and I put them on the quiz as little definitions, not really hints. But A is symmetric when, I'm going to underline that, symmetric when A is equal to A transpose. So this is something we've seen before. A is orthogonal when we have P inverse is equal to P transpose. So that's kind of a weird guy right there, but why did I put P and an A right there? That was wrong. That's a P. Why not? They had P in the book instead of A there. Whatever. So those are some definitions. Let's utilize them in a proof. So I say prove that if A is an orthogonal matrix, then AT and A inverse, so A transpose and A inverse, are also orthogonal. Okay. So I know that A is orthogonal prove that these guys are also orthogonal. So orthogonal. We got A inverse is equal to A transpose. This is my for sure set in stone, we're good to go. If this is the case, this is true. If that's the case, what about these guys? So what I'm going to do is I'm just going to insert A transpose wherever there was an A. Because, well, why not? So wherever there was an A, I put an A transpose instead. Now I'm going to simplify it some. Well, this one here is just a mess. We'll talk about that here in a second. Transpose should be just A. What happens is that I actually take this inverse, and I'm going to inverse both sides. Now, that sounds kind of weird. I'm going to inverse both sides, and inverse actually cancel one another. So what I get is A transpose is equal to A inverse. True. See, look, we already have that. True. Okay, so now let's do it again. And I'm going to insert my inverse. Same thing. Well, we know that inverse is just A. What I'm going to do here is I'm going to transpose both sides. Okay, I'm not going to write that, but you see I'm going to transpose both sides. And we get this guy. True. Done. That was super easy. Okay. Last section. 7.4. Of course you know it. Applications. So I have nothing new to say about this section. I think it's pretty cool, but, well, let's just do it. So I wanted to do something similar to what was on the quiz. So this is a similar question to what's on the quiz. Thought it'd be helpful to y'all. I have this big conic. Actually, it's a conic. It's in quadratic form. It says find the eigens of A, and then find the P so that it's diagonalizable. So here are two things. I want the eigenvalues, eigenvectors. And then I want to make sure that we can do this guy. Why does that say a T instead of an inverse? I don't know if that's a T or if that's supposed to be an inverse. My math is all going to be the same. It's kind of weird. I think that's an inverse. I think I mistyped that, misprinted that on my, on my paper here. Miswrote it. Either way, I'm looking for that matrix that's going to make it similar, diagonalizable, and all that kind of stuff. Okay, so let's start with the eigens. That's actually the big part. This part's really small. As soon as you get the eigens, you're good to go. So what I did, and I actually say this on my quiz answers for this chapter, I say, hey, I use example 6 in the book to kind of help me out. So I'm going to write that here as well. Use example number 6 in the book. Now, example number 6 in the book is talking about the rotation of conics. And that's not exactly what we're doing here, but we have a conic, and they're looking for eigenvalues, and they were doing the same thing, so let's piggyback on what they're doing and do it. It's just a very particular style of how to approach this, and so I want to make sure that we don't mess it up. Immediately what they do is they just say, hey, your A matrix is equal to, and I'll just go ahead and write it up here so that everyone's totally confused. Perfect. Can you see that this goes to this? Now that's the part that took me a while, because they have their, their style conic, and then there was one from the quiz, and then there's this guy here, and so what's going on? How do I actually find this guy? Let me use a different color to show you some stuff. Positive 2, positive 2, negative 2, negative 2. So that's easy, okay? Notice that we got a 3 right here. And then I got 3 halves and 3 halves, right? What I'm doing is I'm splitting it up. The way they had it in the book, I think, was a 16, and so they had 8 and 8. Or on the quiz, maybe there was like a 6. So you got 3 and 3. Well, we don't have a very nice number to just split in half perfectly, but we do have this, and so that's going to be okay. So now you can see kind of where I got this matrix from. From here to there, just do it. Just do it. That's kind of the style. You're wondering, where's that 10? It'll come in later. So what I'm going to do from this is actually find my eigenvalues using the determinant method. This guy, that formula, basically. So let me actually set that up. I'm going to say then I got the determinant of... Now, lambda I is kind of funny because it's lambda lambda 0, 0. This is a 2 by 2, you can see that. And then minus my original. And that whole thing equals 0. So this is my lambda I, essentially. I just distributed my lambda into my I, my 1, 1, 1, 0, 0, 1. Of course, you can merge these. I guess I don't even have to use the matrix form anymore. So lambda minus 2, negative 3 halves, negative 3 halves. And then I got a lambda plus 2. This should equal 0. Well, a 2 by 2 determinant is actually not too bad. And this is something that we've been doing for a while now. So I'm going to say, you know, cross multiply and then subtract this guy there. So I got a lambda minus 2, lambda plus 2, minus negative 3 halves times the negative 3 halves. And this is actually where I messed up pretty badly because I didn't realize that 3 negatives still make a negative. I know it's a little math. So, like, it happens, okay? So watch out for those kind of things. You're like, I was going through my matrix thing, and I'm not getting my eigenvectors, and it's just not working. What did I do wrong? Well, I actually messed up way up here. And so it affects everything else, of course, going downwards. When you multiply these guys, I actually get lambda squared plus 2 lambda minus 2 lambda, and minus 4, 3 negatives. And it's kind of another thing I messed up on. I said, oh, multiplying the 2's cancel. Well, no. You multiply the top and bottom separately. And so it's a negative 9/4. Okay? Well, these guys cancel, obviously. And so what I'm left with is this stuff here, which actually ends up being 25 over 4 when you use your calculator, of course. Move that over, square root it. I get plus or minus 5 over 2. And those are my eigenvalues. Those are my eigenvalues. Okay, so now you saw me find them using that method. So eigen 1, I'm going to say is the positive 5 halves. What I'm going to need to do is I want to find the eigenvector, I use x a lot of times, that's associated with that. I know for sure that we have this guy. So now what's the vector that's also with it? So now basically, I'm saying, what's my eigenvectors? One for each of them. And so the other formula that I have to use is lambda I minus a times x is equal to 0 vector. That's my eigenvector. What I need to do is actually go and find it. So how do I do that? Well, I know that my lambda is 5 halves. So what I actually have then is, again, the long way, this guy minus my original, I don't even always remember. Okay. Times x is equal to 0. When you start shoving it all together there, we got 5 halves minus 2. Actually, I didn't even find out what this was. I just put it all into the calculator, but, you know, that's okay. 2 negatives make a positive 3 halves. 2 negatives make a positive 3 halves. 5 halves plus, why do I have a negative right there? Oh, I'm sorry, this is a positive. Here, let me erase it. Sorry. That should be a positive. I was looking at the wrong place. Sorry. And then plus 2 times x is equal to 0. This is actually a system of equations, essentially. If you really wanted to see what's going on, I'm saying, and I don't really know what these values are, but I got this much x plus this much y is equal to 0. This much x, this much y is equal to 0. Solve for x and y. It's just a system of equations. Well, you know what to do here, right? Probably should have found out what these numbers are because I have to keep on just rewriting it again. I augment it with the zeros, and I RREF. That's what I'm going to do here. So I did that. And I'll show you what I got. I got 1, 3, 0, 0, 0, 0. Now here's something to keep in mind. And this is where I noticed that I was doing something wrong. Way back up right here. I was doing my simple math wrong. How did I know I was going wrong? Well, because I had my answer from the calculator was this guy. This is not good. It's kind of weird because your eigenvectors come from dependent matrices. Notice that this one's dependent, right? It's got a 1, 3, 0. Kind of weird there. So then what is my actual vector going to be from that? My eigenvector, 1, should actually be -3, 1. You're wondering, why did it's a negative right there? Well, again, this is x. I guess y equals 0. So that's a 3. That's a 1. I'm trying to solve for x. And so when I move this over, it turns out that x is equal to -3y. What is y equal to? It's not 0. It's not 1. It's not infinity. Y equals y. It's 1y. You can see my vector now. Okay? So there you go. That's actually one of your answers. It's associated with your lambda 1 being the positive high of halves. So these guys are tied together. Okay? Let's do the next one. -5 halves. I'm going to just cut it quicker. So -5 halves minus the 2. 3 halves. 3 halves. Right? Yeah, 2 negatives make a positive. Yeah. Okay. -5 halves plus the 2. Augmented with 0, 0. RREF. What do you get? And I got out of this 1, -1/3, 0, and then 0, 0, 0. Cool. So then my eigenvector number 2 should then be actually a positive 1/3, 1. Again, this is associated directly with my -5 halves eigenvalue. This eigenvalue has this eigenvector. This eigenvalue has this eigenvector. So now I got my eigenvectors. Phew. So basically I'm done now, right? Well, if you go back, yes, do the eigens, but then also this thing, okay? And again, transpose or inverse, I don't really remember. They might actually be the same because it was diagonalizable, and so they're equal to one another, so it doesn't really matter. Blah, 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 blah. We're just wanting to find out what is P. What is that arbitrary P that we've been talking about with the similar matrices all the time, or we can find right now? They also want it normalized. And so it's going to be the normalized eigenvectors. Like an eigenspace, kind of. But normalized. What does normalized mean? Is that you're dividing by the magnitude. And so, what is the magnitude of this guy here? Well, just on the side, let's talk about it. Square root of 3 squared plus 1 squared. Negative, positive, doesn't really matter. So, we got the square root of 10, basically. What's the magnitude for this guy here? Well, it's the square root of 1/9 plus 1, 10/9. When you do that, it's the square root of 10 over 3. That's your magnitude. You're dividing by these magnitudes. Dividing by them. So you're going to divide by the square root of 10, and actually here as well, the square root of 10 is going to go in the bottom, but that 3 will actually come to the top. And so here we go. Originally, I had -3, 1. Well, it's going to be -3 divided by square root of 10, and 1 divided by square root of 10. That was that magnitude for that one. This one here, I got the 1/3 divided by, and this is really funky, square root of 10 divided by 3. And then I have the 1 divided by the square root of 10 divided by 3. Well, I mean, this could be way cleaned up, because, like, that's almost bad math. Almost. So then I want to clean this thing up a lot better, if that's okay. This one's super easy already, just whatever. I know you were taught to, rationalize denominator. You don't need to do that. You don't need to do that. Those 3's cancel, and so you got the 1 over the square root of 10. And here, that 3 comes to the top, actually, as a positive 3 over the square root of 10. And that, actually, hold on, do I have negatives over there? Why do I have negatives on my answer? I don't know why I have negatives on my answer. That's weird. I don't think it should be negatives. Okay, well, there you go. I'm not perfect. Good enough for me. Cool, huh? Very cool. I think we're done here. We're done with the recordings for this class. If you have any questions about any of this stuff, please let me know. I want to be here to help you. So thank you very much for listening and going through all this with me. And have a great day.